All right, welcome everyone to our last session for the group actions in differential geometry for the MCA 2021. And our first speaker of today is Emilio Lauret from Universidad Nacional del Sur in CONICET, Bahía Blanca. And he will speak about diameter and Laplace eigenvalue estimates for left-invariant metrics on compact Lie groups. So yeah, thanks, Emilio.
Okay, thank you, Ramiro. I'm very happy to participate in this conference from Quilmes, from Totoral, my hometown, later than in Buenos Aires. It's another advantage of these virtual events. I wish to thank the organizers, Caroline, Romina, and Ramiro, for this great session and the opportunity to speak here. Okay, let's start with stating the problem after some standard conventions of notation. Do you see my hand, right? Yes.
Yes, we see it.
Okay, let's fix capital G, a compact connected Lie group of dimension n, because G is the algebra, and fix a bi-invariant metric. You know that the left-invariant metrics on G are in correspondence with the inner products on the tangent space and the identity, which is identified with the algebra of G, and denote in this way the inner product corresponding to this fixed bi-invariant metric. And again, the inner products are in correspondence once an inner product is fixed. This is in correspondence with positive definite symmetric endomorphisms with respect to these inner products, right? And the correspondence is given in this way. You know very well that. I am going very fast, but this is the idea. A left-invariant metric corresponds to an inner product, and there is always an element there, okay? And well, this is some notation. If you pick now an element here, positive definite symmetric endomorphism, we will denote in this way the corresponding left-invariant metric and inner product. Okay. And let's denote by mu1, mu_m the square root of the eigenvalues of this operator, right? This is positive definite symmetric operator, so the eigenvalues are positive. We take the square root. That's why the square is there, right? And we will call this the metric eigenvalues of the metric G, of the left-invariant metric G, right? And the goal is to estimate in terms of these numbers, of this eigenvalue, the square root of the eigenvalues, these two objects, right? The diameter, which, as you know, is the maximum distance between 2 points, the Riemannian distance associated to this left-invariant metric, and lambda1, the first eigenvalue of the Laplacian. Okay, if you to the purpose of this talk, it's not necessary to give the definition of the Laplacian, the Laplace Beltrán operator. Just think that it is an important number, right? It's important spectral variant with many related with many analytic aspects. Okay. The motivation to study these two objects is, well, first of all, this functional that associates the Riemannian metric in principle arbitrary to the product of these objects. Here is the square of the diameter, is invariant by positive scaling. There are many estimates for lambda1 in terms of the diameter, right? Which, in fact, there are lower bounds for this function. Okay, the usual assumption for this is lower bounds for the Ricci curvature. Okay. But in this context, we will work for homogeneous manifolds. And Peter Lee in 1980, 40 years ago, prove that for every compact connected homogeneous Riemannian manifold, one has this estimate. Okay, so this is bounded. This term is bounded by pi squared over 4.
Emilio,
And this constant doesn't depend on the dimension. Yes.
quick question. Given an isometry class of metrics, are these mu1, mu(n) unique? The eigenvalues?
Yes, 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 sure. Sure. Yes, 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 yes.
Up to isometry.
Up to isometry. Yes, yes, yes.
Okay.
I mean, there are left-invariant metric with the same metric eigenvalues, but they are not isometric, right? They, in general, do not determine the metric. Okay.
But two isometric
That's what
metrics
you
have
mean?
the same eigenvalues. Okay.
Yes, yes,
Okay.
yes. Okay. Well, the theorem by Peter Lee is a lower bound for this, universal in the sense that this constant doesn't depend on the dimension of anything. You are, of course, assuming homogeneous, but remember that the Ricci curvature is not bounded by below in this context, right? So it was a surprising result. And well, one can ask, it is natural to ask, what about an upper bound? And an upper bound doesn't exist. It's pretty easy to check. I mean, the most simple example, a round sphere have, if you pick, for instance, the unit sphere, the dimensional unit sphere, the diameter is, of course, pi, right? The distance between the poles. And the first eigenvalue is d, of the Laplacian is d, and this goes to infinity when d does it, okay? So there is now an analogous upper bound for this, but it is not known what happens if we fix the dimension, right? Because in this counterexample, the dimension is going to infinity, and it is open what happens when you study the compact connected homogeneous Riemannian manifolds of a fixed dimension. It is not known whether this is bounded by a bound, this function, okay? Recently, I mean, 3 years ago, 4 years ago from archive, there is a first step to study this question, and it's in the case that we saw in the previous slide. You fix a compact connected Lie group, and you ask for, I mean, this is a conjecture, the Eldredge, Gordina, and Saloff-Coste conjecture that this is there is an uniform upper bound among left-invariant metrics. Okay, these terms, I have the zoom, that's why I cannot touch this part, sorry. But this term is bounded among left-invariant metrics on the compact Lie group G. Okay, for any G, but this upper bound depends on the Lie group. That's a conjecture. Okay. And the motivation, this is of course a motivation of why to study these two, why estimate these numbers. And about the conjecture, well, actually, Saloff-Coste gave a talk in this last week in this conference, very nice. They conjecture actually that they proved that this upper bound when G is uniformly doubling, and this means uniformly doubling. Okay, up to here, you fix a metric, and this is doubling, volume doubling. Check that this is the volume of a Riemannian ball of radius to r. R, of course, here is x, but doesn't depend on x because we are in a homogeneous context. But the main issue here is that the supremum is over every left-invariant metric on G. Okay, that's why uniformly is in this one. Okay, and this is a more analytic problem. A consequence is the previous conjecture, and they indeed conjecture that every compact connected group is uniformly doubling. And it is pretty simple to see that the torus is uniformly doubling because it's locally Euclidean. I mean, the torus, any left-invariant metric is flat. So it's Euclidean locally, and it is simple to check this. And they prove, the three authors, they prove in the same paper that SU2 is uniformly doubling. Okay, the previous conjecture is proved when G is the particular cases known so far are G abelian, I mean a torus, and SU2 and SO3. They didn't consider, but in a very similar way is follows. And these are the only cases known so far. Okay, abelian, I mean a torus, SU2, and SO3. Okay. And let's talk about the three-dimensional case. I mean, in the non-commutative case, these are the only cases so far. And from a Riemannian point of view, these are very special, right? Because one always associate to a left-invariant metric, and actually in the isometry class, these numbers. Oh, now I am thinking in Ramiro's question. Well, I mean, one always has associated to Riemannian metric this number, the metric eigenvalues, and these cases are very special because this number determine the metric. Okay, this is not true in general, but this number determine the metric. By the way, Ramiro, currently I am not sure if if it is true what I said before. If you have two isometric left-invariant metric, they have the same eigenvalue. I'm not.
There's the automorphism group acting, right? So by yes, multiplication, by conjugation, but there's a transpose. I'm not sure that the eigenvalues will be the same.
I'm not sure. I will think about it later. But the main point in this case is this number determine the metric. Okay, up to isometry. This is up to isometry. This number determine the metric up to isometry. And well, I was able to prove a couple of years ago these two estimates. I mean, the lambda one for SU1, SO3, and the diameter independently, in terms of these numbers, in the three-dimensional case. And check that always only mu2 is involved, right? Only mu2. Remember, the goal was to estimate these objects in terms of these numbers. In the three-dimensional case, this is the case. And if you multiply this times the square of this, check that the mu1 cancel, because here you have a square, diameter square, right? So you obtain an upper bound and a lower bound that holds uniformly for every left-invariant metric. This is an alternative proof of the proof of Eldredge, Gordina, and Saloff-Coste for SU2, and also calls for SO3. Okay, and well, the idea why I started to think in this is to extend this strategy to bound in terms of this number these two objects independently, and see what happened for other groups, right? And well, the conclusion is, in the only way that this strategy works well is for SU2 and SO3. Okay, but there are some partial answers that are interesting enough. Okay, and here we have this is a theorem that is a little better than these numbers. It's not important. So let's see some simple estimate. Fix a possible definite symmetric endomorphic, which induce, of course, a left-invariant matrix, abbreviate UK the eigenvalues, and of course you have a decomposition in eigenspaces, one-dimensional decomposition in eigenspaces, right? You have this phi is written. Remember the eigenvalues of this number are mu1 square, mu2 square, etc. And you always have this decomposition. It is not unique if you have multiplicity greater than 1 for some eigenvalue, but fix anyone. And well, since we have the eigenvalues ordered in this way increasingly, you have this, right? Mu I is less than or equal to mu m, and the same for mu1. And well, this number doesn't depend on the parameter, so you have this, right? This is not very clever, but it is useful to have the following. There is a lemma, not difficult lemma, that says that if you have these inequalities between two elements here, means that this minus this is positive semi-definite, you indeed have a lower bound for the whole Riemannian metric, and by monotonicity you have the same inequality for the diameter. Okay, it's not difficult, but there are some steps. And the reverse inequality for the first eigenvalue. And well, you obtain, using this inequality, you obtain that the diameter, for instance, of this is less than or equal to this. And please believe me, here are some constants, believe me, with some very standard steps. One takes out this constant outside. Okay, so you have the diameter of the left-invariant metric that you fix at the beginning in terms of the diameter of the bi-invariant. Remember, a compactly grouped endowed with the bi-invariant metric is a symmetric space. So in principle, one can compute in more or less explicit way the diameter and the first eigenvalue. Okay, and you have here the eigenvalues mu1, mu(n), and so on. Okay, and well, I copy and paste the previous two rows here. And well, the idea is the following. We get this in the upper bound mu(m) here, but well, one wish to put an index here, k, with k as small as possible, right? Because m is the largest index, mu(m) is the largest of these eigenvalues, so whether it would be interesting to put here an index as small as possible and here an index as large as possible, right? And more or less the same here, but in the reverse order. That's the goal, the more precise goal. And of course, this should hold for uniformly for every left-invariant metric, right? And well, this is the main theorem. Let's assume G non-abelian because the abelian case is simpler, but not the same statement. And pick this strange index. K max will be 1 plus the maximum dimension of a proper closed subgroup. Okay. And well, the theorem said that there are positive constants obtaining this. Okay. I mean, remember here used to be an m, an index m, and we proved that we can go down to the index up to the index k max, right? And here used to be a 1 and now a 2. Well, but let's see that why is the word optimal there is because, check for instance this case, k max. If you put k max minus 1, the previous index to this one, this is not bounded. I mean, this over this is not bounded by above. So there is no such C2 when you put k max minus 1 here. Okay, so this k max is indeed optimal, the optimal index that this can hold. Okay, and well, here there is a 4 here, which means that the optimal index is 2 or 3. I was not able to prove which one is the optimal, but in the semi-simple case, we have a 3 here. So the optimal index is indeed 2. Okay, when G is semi-simple, which is the case that I am more interested in. And I guess actually that in the general case, there should hold here for 3, but I was not able to prove. Okay,
Emilio?
Yes,
Emilio,
tell me.
do you use add H invariant metrics to prove these things?
Yes. Unfortunately, I was not have the time to prove more or less the idea. There is an adequate H and an adequate variation for this metric that gives this these things, but I will not talk about the proof.
Okay, okay, but that's the way H is involved. I mean,
Yes, yes, yes,
Okay.
yes, yes.
okay.
Okay. So again, I copy and paste the two rows here, these two rows, the main estimates here. And now, if you multiply this times the square of this, that remember, this is the object that we want to bound by above, we get this. And of course, this is not bounded by above, and this is not bounded by below, by a positive number, unless K max is 2, right? If K max if the index K max is greater than 2, remember they are ordered increasingly, this is not bounded by above. And well, the bad news is that the quality K max equal to 2 only holds for SU2 and SU3. Okay, that's the conclusion. This strategy only holds for the cases that were already previously known. But we are able to give a partial answer to this conjecture. Let me explain very quickly. If you fix the composition in one-dimensional subspaces, remember before we fix a positive definite symmetric endomorphisms, and we fix the composition in one-dimensional eigenspaces. Well, now we are fixing this decomposition, and pick K, the index, such that the sum of the first K summand is bracket generating. There is a notion of bracket generating very important in analysis, in sub-Riemannian geometry, but in our context, this means that the subspace Lie generates as the whole algebra G. Okay, there is no any proper subalgebra containing this subspace. This means bracket generating in our context. And the theorem said that there is a positive number, there is an upper bound for this term, but holds not for every left-invariant metric, hold for under certain conditions. That if you want to read it, you are welcome, but here let me explain in a more graphic way. Here, this is the index K, the same index K here. This is an M times M matrix that in the diagonal KK entry you have a mu, any number, and here you put the rest are 0, of course, and here you put any positive definite symmetric endomorphisms or matrix. But with the spectrum, with any eigenvalue there is less than or equal to mu, and more or less the same here. But every eigenvalue is greater than or equal to mu. Okay. Of course, this is strictly smaller than the space of left-invariant metric, right? But in this particular case, when G is semi-simple, there are two-dimensional spaces that are bracket generating. This might be surprising the first time. It's surprising to me, but in G semi-simple, there are two-dimensional subspaces that are bracket generating always. Okay, and well, check that the dimensions is, of course, the dimension of this space is strictly smaller, but it's not at least has the same order of growth, right? That is m squared over 2. So it is quite big and might be considered as an evidence of the conjecture. Okay, and let me finish with some advances in the second paper in the homogeneous setting. I mean, this question can be thought besides G to pick now a closed group of G and consider the metrics on G over K, the homogeneous space, which are G invariant. And you ask whether this functional is bounded by above or by below among G invariant metrics. Right? When K is trivial is the case that we saw previously. And well, it turns out that the original conjecture implies this conjecture for every case. I mean, you pick a compactly grouped G that the original conjecture holds. Well, this implies, well, not immediately, but it implies that this it holds for every K. In this context, the main difference here is you have easy cases because the space of left-invariant metric on compactly groups is very difficult. Even in SU2, the proof were quite difficult. But here you have, for instance, the cases when the homogeneous case is isotropy reducible, right? For instance, in reducible symmetric space, and in this case you have only up to scaling, you have only one metric G invariant, G over K. So this is constant, in particular bounded, right? There are easy cases in this homogeneous setting, and well, it could be proven that when the homogeneous space is the isotropy representation is multiplicity free, this upper bound holds. Okay, this means that if you take any decomposition of the isotropy representation and the summas the terms are mutually inequivalent, then you have the upper bound that you want. Okay. Well, that's all. That's all. I have one slide more, but it's not important. I stop here. Thank you very much.
Thanks, Emilio, for a very nice talk. And are there any questions or comments for Emilio? So you mentioned you had an extra slide. Why not looking at that one?
Well, this only consider the case of a compact symmetric space of rank 1. You pick any of them, simply connected, so the spheres and projective spheres, projective spaces over the complex, quaternionic, and Cayley plane, and you pick any homogeneous metric in any of them of a fixed dimension, and the upper bound holds for these cases. And the proof was just the application of the previous cases, excepting for one case, which is this one. This is spheres that one have to work a little bit. That's all. Not essential to the talk.
In the last slide, the theorem, that the constant C is an existent result, or you can say more or less what is C in terms of G over K?
Well, the constants are not explicit at all. I would like to respond the question here in the group case. No, this depends on. I haven't talked about the proof. That's the point. But this depends on the diameter of some sub-Riemannian left-invariant structures in G. Okay, so they are theoretical. I don't think it is possible to compute explicitly these terms, but it is involved here in these four constants are involving sub-Riemannian structures, left structures on the compactly group, and also singular Riemannian structure, which means that the inner product is positive semi-definite. It might be some parts where the inner product is zero. So that you have curves in the compactly group which distance zero. You go for free in some directions. It's a strange context. And in the sub-Riemannian case, you have the opposite. There are some directions that you cannot go, because if you go a little bit, the distance is infinite.
So they are in principle in geometric terms, not
Yes.
not in algebraic terms yet.
No.
Okay, thanks.
Further questions? Well, I was going to ask how do you prove these results, but I guess you mentioned already that this involves looking at sub-Riemannian geometry. Can you say a few words?
Yes. Well, probably the best thing is to advertise a talk in the third Geometric Analysis Festival. As Ramiro, we gave talks which are available in YouTube, and it's an interesting thing because you don't have a time bound for give this talk, and I gave more details there. Probably this is better. But
Okay.
Oh, you are YouTubers.
yes.
Okay.
But we are not earning
Congrats.
money because of this talk.
Congrats.
Any other questions for Emilio? Well, if it's not the case, then let's thank him again for a nice talk.
Very interesting talk.